Welcome to this video on the topic of vectors. In this lesson, we're going to have a look at how we can mix geometry, vectors, and algebra to solve geometric problems. Now, the specific skill that we're looking at is how we can find unknown quantities by simply representing known quantities as dilated vectors. Let's have a look at what that means by example. Consider that we have points O, A, B, and C, and if we connect them all together, they form a rectangle. We have two more points. First one, point N, lies in between points B and C, such that it marks a midway point. Point P lies upon a line that could be drawn between points A and C, as well as a line that can be drawn between points O and N. So point P is the intersection point of these two lines. Now, given that point O represents the origin, the position vector OA could be written as A, and the position vector OC could be written as C, we would like to describe the position vector of point P in terms of vectors A and C. So quite a lot going on here. To state again, we're trying to describe the position vector of point P in terms of vectors A and C, or in other words, point P in terms of getting to point A and getting to point C. Now, as a disclaimer, this is quite a long process to do. However, once you get the hang of the steps and the mode of thinking that we're using here, these problems become quite straightforward and the knowledge is transferable to a number of different domains. Now, first thing we're going to do is we're going to think in a very broad sense. What we're going to do is we're going to start off by simply thinking about ways in which we can pass through point P. Once we think of ways in which we can pass through point P, we're then going to start thinking of ways in which we can move toward point P and actually stop on point P. And then once we've done thinking about ways in which we can stop on point P, we're going to think of ways in which we can describe P explicitly. Now, starting off, let's label our diagram. We know that O represents the origin, O to A represents vector A, O to C represents vector C. So we have two new vectors, A and C. Now, additional to this, we have the pathway from point A to B. This is the same as vector C because they point in the same direction and they have the same length. Similarly, the pathway from C to B is just vector A, same length, same direction. Okay, next, let's think about ways in which we can pass through point P here. Suppose we start off at the origin. The first way in which we can pass through point B is we can start at the origin and then just travel along this line over here, finishing up at point N. Point N, of course, being the midpoint between points C and B, or in other words, these two lengths here are equal. So what we're going to do is we're going to write an expression that describes this pathway here. So O to N can be described as, firstly, let's go from the origin and travel across to point C, which gives us C. And then let's travel upwards from C to B, which is A. But remember, we're not going all the way to point B, we're going halfway up B, which is at N. So it's going to be dilated by a half. So there's our first equation. Okay, next equation. Let's think about, suppose we started at point C, we could travel through point P by traveling up to point A. So let's build an equation here. How do we go from C to A? To do this, we start at point C. We could travel upward through vector A and backwards against vector C, or we can travel backwards against vector C and then upwards towards A. I'm going to take the second route. Negative C plus A. And thus we've discovered two ways in which we can cut through P. Okay, next step, what we want to do is we want to start thinking about how we can stop at P. So removing these lines, the first one I want to do is I want to think about traveling from O to N, but this time rather than going through P, I'm going to stop on P. Now this is where the idea of dilating vectors comes in. Suppose we want to go O to P. We're going to travel in the direction of O to N. However, we're not going to travel all the way across O to N. Rather, we're going to travel K distance along, so dilate it by K, where K is just some non-zero number. Now expanding upon this, we're going to open ON up in terms of what we described as before, so KC plus a half of A, and then expanding that out, KC plus a half KA, and there's how we go from O to P. However, it's algebraic at this stage. Let's think of the other way, C to A. We already know that to travel from C to A, we're going to pass through P, but we want to stop at P in this instance. Next, rather than starting at C, what I'd like to do is I'd like to start at point O. So I'll start at point O, travel to point C, and then from point C, I'll travel upward to point P, where I stop at point P. Let's build this vector equation here. Going down, I want to travel from O to P. In this instance, I'm going to start off by traveling along vector C. Once I've finished traveling along vector C, I'm going to travel upwards along vector CA as defined here, as shown here. However, rather than traveling all the way up to point A, I'm going to stop at point P. So I'm going to dilate this vector by a value of M, where M is just some non-zero number. Expanding this out, the definition of vector CA is just minus C plus A, expanding the brackets, and then factorizing for C. And there we go. We have another expression that describes how we go from point O to point P. Now we have two equations and two unknowns. The way in which we're going to solve this is, firstly, we're going to turn these two equations into a single equation by acquainting them. Okay, so now it looks like I've turned two equations, two unknowns, into one equation, one unknown, but what I've done here is going to make it in such a way that we can actually do something. If you pay attention, you can see that there's a C over here and one C over here, and a K over there, sorry, an A over there and an A over there. The way in which this works is because both sides of the equation are equal to OP, then what that means is the coefficient in front of vector C here has to be the same as the coefficient here. Similarly, the coefficient in front of A has to be the same as the coefficient on the right hand side of the equation as well. And because of that, we can turn this equation into two smaller equations. So it will be K equals 1 take M. That's our first equation. Our second equation is going to be half a K equals M. Now it doesn't matter which one of these we choose to work with, we just have to rearrange one and sub it into the other. In this instance, I will work with the second one and say M equals a half K. I'll go back to my first equation. I'll solve for K, and therefore K is going to equal 2 on 3. Since I know the value of K, I can now solve for the other one. So let's go. M is 1/3. So now we have the two values that define our equations over here. Next, what we need to do is we need to sub the values of K or the values of M to find the definitive value for the direction vector for point P. We can do this one or that one, it doesn't matter. I'm going to do this one, KC plus a half KA. And thus we arrive at the position vector that describes point P on this diagram up here. So point P is equal to 2/3 of the way along vector C and 1/3 of the way along vector A. So in other words, we're going to split 1, 2, so split vector C into 3 parts. It's going to be 2 parts over here, and then we're going to split vector A into thirds again, so we're 1/3 up. So we're going 2/3 across C, 1/3 up A, and that arrives at P. So in summary, what we had a look at in this particular video was we were looking at how we can mix geometry, vectors, and algebra to be able to do geometric problem solving. The method that we learned today was how we can dilate known vectors to find unknown quantities, in this case finding position P, given that we knew vectors A and C. The way in which we do this is we start off in broad terms and we make general statements about how we pass through the point that we're trying to get to. After we've made general statements about how we pass through the point, we make statements about how we stop at the point, in which case we dilate known vectors. From there, we build as many equations as we have unknowns, we sub them all together, and then we just solve simultaneously. Once we get the values of the unknowns, we can sub them back into any of the equations that describe how to stop at that point, and it will reveal the equation, or it will reveal the position vector that describes how to get to that particular point in space.